So good afternoon, my name is Dorian Perkins, and I'm a PhD candidate at UC Riverside, as was just introduced. So today I'm excited to present to you Simba, a cloud data sync infrastructure for mobile apps, which eases app development by providing tunable end-to-end data consistency. And this work was done with my mentors at NEC, Nitin and Akshat, some collaborating students, Curtis and Younghwan, my advisor, Harsha, Madhyastha, and Cristian from NEC. So today, mobile apps often use cloud-based services to enable sharing of data among users and to offer a seamless experience across devices. Many of these apps are data-centric apps, as we call them, since their primary function is to generate and consume data, both locally and remotely. Some of you may be using some of these apps right now instead of listening to my talk. It's okay, I understand. I know Candy Crush is addicting and it's right before lunch, so your attention span is short. But the key point here is that with these types of apps, data is king, and these apps must be absolutely good at handling it. So what does it take to build a data-centric app? So to set the stage, let's walk through a construction of a sample photo sync app. So first, an app must create a GUI and define some activities such as storing and viewing photos locally. Then we must define a cursor adapter to access data, such as the album info in the local database. And on Android and iOS, this is typically SQLite for tables. And then we'll store photo objects in the local file system. So I should note here that the app will need to provide the app itself must provide the unified data model across these stores. And then the app will also have to provide sync across multiple users and devices. So this requires using some custom sync methods, probably using REST, and also providing some network management. Then the app may want to push notifications when new data is ingested, or implement some kind of caching for efficiency. And now you can imagine how hard it would be to manage both user data and ensure consistent sync. So what happens if photos appear but there's no metadata? Or vice versa, if metadata is there but there's no image? And even if you wanted atomic updates, you may not want to send table and object data together for efficiency or network costs. So you can see how all this can quickly become tedious. So it's no wonder that some companies spend a small fortune to make sure that their apps are solid before they are widely released. But that's not all. So on top of this, in addition to the app logic, developers also need to have a cloud service to coordinate syncing across multiple devices. And this cloud service should mirror the application components, provide a scalable data store, handle multiple clients, and a variety of other components that I've listed here on the left-hand side. So the summation of all these tasks is it's clearly a lot of work. And if you think this is too much for a single developer, you're probably right. So there's a need for infrastructure services that manage mobile data and such that developers can build a high-quality app. So as I showed on the previous two slides, writing a data-centric app is onerous. So let me distill the key technical challenges which we must overcome. So first, apps must manage a partitioned data model where objects and tables are siloed into different data stores, and there's a need for atomicity across this interdependent data. So there's a lot of great work on trading off consistency in the data center. But in mobile, there's a fundamental need to ensure consistency end-to-end across devices in the cloud. So this is hard due to things like local and network failures, disconnections, and limited bandwidth. And apps also have diverse consistency requirements, which are often dependent on the app's data or the app logic. And there's also a desire to support disconnected progress. So we find in practice some apps just simply disable offline writes. However, allowing the client to make progress while disconnected requires a more robust protocol which provides conflict detection and resolution. So now that we understand the challenges of building data-centric apps, let's see what's available to developers today. So thankfully today, there's a great trend in building solutions for mobile data and it's motivating that others are looking into the same problem. So modern day sync services like Dropbox, Box, and iCloud provide APIs for apps to sync objects. Additionally, recent companies like Parse, Kinvi, and KeyCloud provide the same thing for syncing tables. So this model is quite useful for mobile apps and is gaining a lot of traction. However, to kill the suspense, no, these are also not sufficient. So these provide either object-only or table-only sync. And with no atomicity guarantees across the interdependent data, and they also commonly only have eventual consistency. So if even the existing services don't cut it, the question remains, how can one achieve a high-quality data-centric app? So with that, I hope I've now convinced you that building a high-quality data-centric app is no walk in the park. So we were curious to how current apps handle this challenge. And next, I'll give you a glimpse into our findings. So before we set out to fix current issues, we wanted to first make sure what was broken. So we performed a study on how several popular apps handle ensuring consistency under different kinds of failures. So we focus on end-to-end consistency, which is observed by the user under concurrent operations and disconnections. And what we found wasn't appealing. So we tested several apps that use tables and objects and covered a range of app categories. And some apps implemented their own mechanism, while others used existing services like Dropbox, Parse, and Kinvi. And to perform the test, we used two devices, both of which performed updates and reads. And we tested for disconnected operations while both devices were online, and concurrent operations while both devices were online, and when one or both devices were offline. So let me describe our findings for a couple of these apps. So the first app you might recognize is a note-sharing app called Evernote. And Evernote allows users to embed rich media into their notes. And their tech blog claims that there are no dangling pointers possible. But guess what we found? In fact, we were able to create dangling pointers by forcing a disconnect during the sync of a rich media note with embedded objects. And this is supposed to be a popular commercial app, and it should be pretty good. And next we have an app called Hayu, which is a grocery list app that supports sharing. Here we found that due to last writer wins semantics, we were able to cause data corruption and resurrection of deleted data. And also upon conflicts, the user was not always notified. So it turns out that even for apps that use existing sync services, the verdict is not so good. You could end up with double, missed, or even wrong purchases. So in other words, you might end up with 2 gallons of milk but no cereal. So overall, we find that today's apps are often inadequate in terms of their consistency. And we've condensed our findings into 5 key points. So the first point is that apps have diverse consistency requirements. So we observed different consistency even for different types of data within the same app. So also sync semantics were often oblivious to consistency, and this was most common in apps that use off-the-shelf solutions. So mobile apps are not consistent even when they use a sync service like Dropbox. Some apps suffered atomicity violations on interdependent data, so as such, dangling pointers or malformed data was often visible to the user. There was limited offline support for some apps. Some apps hung indefinitely, and other apps just didn't launch altogether. And other apps exhibited inadequate error propagation. So instead of notifying the user, some apps crashed, forced logouts, or even had a loss of in-app purchases in the face of conflicts. So the takeaway here is that data sync needs fixing. And we have more details about this study in our paper. But the question is, how can we do better? So we see there are many problems with current apps, no matter whether they implement their own data management mechanisms or use existing sync services. So what do? Existing services are more or less a black box to the developer with limited programmability, which makes it hard to correctly interpret the developer's intent. So what we really need here is a better sync service. So we need a well thought out and comprehensive solution that provides a developer-friendly abstraction while handling atomicity of interdependent data, synchronization, and consistency all behind the scenes. So we find here that there is an opportunity and a set of challenges to build such an infrastructure which we aim to address through our work. So now I'll describe our solution, Simba, and how it addresses these challenges. So first we implement a novel data sync abstraction called a Simba table, or S table for short. So here I show the logical view of an S table, which is the interface with which an app developer interacts through their app. So under the hood, an S table is physically split into a table store and an object store. And in the table store, the logical photo image that I show is actually replaced by a list of references to its chunks, or its chunk IDs, which are stored in the object store. And the contributions of our S-table abstraction are twofold. So first, we provide a convenient local programming abstraction for developers. And then second, we have a set of nice properties which I previously motivated, such as unifies data model and tunable consistency. So this sounds good, but how far does it really get us? Well, it turns out it gets us pretty far. So recall this slide from the beginning of my talk where I showed you how hard it is for an app developer to implement an app. Well, let's see how easy it is with S-tables. So first, a developer would create a unified tabular and object data table using a create table function. So also note that an S-table is the unit of consistency specification. And Simba's S-tables provide three different options: strong, causal, and eventual. And all rows in an S-table are subject to the same consistency. More details about our consistency schemes can be found in the paper. So next, Simba offers methods for reading and writing tabular and object data. And in this case, you can see that objects are written to and from streams, which is common for mobile apps. But the highlight here is that, so we also register this table for use with the Simba Sync service by registering a read or write subscription. And in this subscription, we can specify the period at which an app synchronizes with the Simba server or with the Simba Cloud and other preferences. But what's really awesome here is now all that complexity that the developer had to deal with, Simba handles that. And Simba is also resilient to disconnections and conflicts. So rather than imposing a drop everything policy, apps can continue to make forward progress and address conflicts later by explicitly invoking our conflict resolution stage. So let me move on to the system overview of Simba. So on the mobile device, we install and run a Simba service, or the Simba client, and apps are written to the Simba SDK, which then connects to the service and synchronizes data over a custom Simba Sync protocol. So Simba provides all the features that I previously talked about, but the takeaway from this is that most of the things that we saw on the left in the original app development slide are now handled by Simba, and the developer can focus on the core logic of his app. So if you're interested in more details about the Simba client, please check out our FAST paper titled Reliable, Consistent, and Efficient Data Sync for Mobile Apps. This is from FAST 15. But in this talk, I'll dive into the Simba Cloud. So zooming into the cloud as expected, we've built a scalable architecture which is capable of handling or managing multiple clients and multiple tables across two different distributed hash tables. So we have a hash table of gateways, which handles the clients, and a hash table, or distributed hash table of storage nodes, which handle the tables. And our backend data storage is actually handled by, tabular storage is handled by Cassandra, and the object storage is handled by OpenStack Swift. But our design is amenable for other existing or a custom solution for these backend stores. And of course, there's many details that I could talk about on how we design the cloud store, But I'm going to focus on a part which I think is most interesting, and that's the sync protocol, because it's what differentiates Simba from other data stores. So why is Simba different? So here I compare an object store such as Amazon S3, which provides gets and puts on distinct IDs to read and write objects. So Simba is a data sync store, and it provides a different interface. Instead, Simba exposes sync operations which return the changes between two distinct versions of a S table. So as such, in Simba there's a need to query by version. And a standard object store cannot simply do this because it requires an expensive scan operation. So there's also a need to find rows that, that match a change set query. So this requires both mapping our versions to the row keys and constructing a change set. And so in the change set, we keep the information about what row data has changed and also what chunks have changed. And last, so we define a change set as the set of all changes between any past version of the table and the most recent version of the S table. So let's see how sync works in practice and why change sets are so vital to Simba's efficiency. So to demonstrate how sync works, I'll go through an example of an end-to-end sync, first upstream from one client and then downstream to another client. And for this example, I intentionally use an update operation. Insert is just a special, simple case of an update. So the S table in this example uses causal consistency. So I start here at a point where all clients have already synced some initial version of the S table. So you can see that they already have a table on the left-hand side and some objects. And this particular client, it wants to make some changes. So you can see that the row ID 1 has some changes, and there's also a third chunk that's been added to the object. So the client next sends the changed tabular data to the cloud, to the store, and the store retrieves the existing table and applies the new updates. Then for any changed objects, the client syncs those with the store, and they're stored in the object store, and the IDs are added into this staged row that's shown under S table. So once the chunks are received, then the store will commit that table data, and a notification is dispatched to all subscribed clients. Downstream sync is similar. So first, a client issues a downstream sync or a pull operation, and it specifies their current version. And this is in response to the notification message. And this tells the store to retrieve the set of changes for that version from that version to the current version. So the store then retrieves the updated rows and sends them followed by the objects. But we have a problem here. Downstream syncing is very efficient since we're doing per row versioning, and we receive the entire row anytime a column is updated. So how can we improve this? So for this, we designed what we call a change cache. And I show this in the upper right-hand corner of the Simba store figure. So actually, upstream sync looks more like this. So once all updated chunks have been received, the updated row is ready to be written to the table store. So as the row is committed, a change set, which describes which row data and object data has been changed, is generated and then inserted into the change cache. And finally, a notification is dispatched to all subscribed clients. So with the addition of the change cache, downstream sync is much improved. So first, a client issues the same downstream sync as before, and the store then retrieves, it looks up what's in the change set cache, and after it looks from whatever version the client specifies to the most recent version, and compiles a list of changes. Then the store can send only the modified changes, or only the modifications between those versions, instead of all the changes for that row. So now that we've overviewed Simba's design and operation, let me dig into some evaluation results. So today I'll cover 2 evaluation results. First, I'll show how Simba makes it simple to write consistent apps, and also show that Simba can scale to handle many clients and tables. So if you're interested in more of the evaluation results, please see the paper. So let's see how Simba can be used to fix some existing apps. So first we look at an app called todo.txt, which is an interactive task list. So this app currently stores two different lists, two lists in two files using Dropbox Sync. So it has a list for active tasks and a list for archived or completed tasks. And we use Simba to port this to enable multi-consistency within the app. So we changed the active tasks list to an S table with strong consistency and the low priority immutable archive tasks to another table with eventual consistency. So and next we took a look at the universal password manager, which we found to have broken consistency due to silent overwrites caused by concurrent online and offline operations. So we ported this app with two different approaches. First, we simply stored the entire database as a Simba object, but this has limited ability for efficient changes. And second, we ported each account to a single row in an S table. So together, both of these ports took only a few hours. So Simba makes it easy to write consistent apps. And in our FAST paper, we implement attempt to implement equivalent apps with Dropbox, but find this is hard. And there's more details about that in that paper. So for the scalability evaluation, we're fortunate to use some beefy nodes at the Susitna cluster at Probe. And I'll show that Simba is able to scale under high client load. So in this experiment, we deployed 32 different nodes. 16 nodes had our gateway and Cassandra deployed on them, and another 16 nodes had our store and Swift deployed on them. And we had 128 tables across these with a 9-to-1 reader to writer ratio and kept the operations per second at 500. So the y-axis measures the client perceived read-write latency to the Simba Cloud, and note the log scale on the y-axis. And on the x-axis, we scale from 10,000 to 100,000 clients. So as you see here, Simba scales as the median latency is stable under 100 milliseconds for all cases. And we also measured the backend storage latency and found that it's stable as well. So the error bars represent the 5th and 95th percentile latency, and we found that at 100,000 clients, this is about 100 clients per core, so we believe this to be CPU oversubscription. So the takeaway here is that Simba scales under high client load. And similarly, Simba is able to scale to many tables. So using the same setup, this is using the same setup as last time, except for the number of clients is 10 times the number of tables. So the y-axis measures the client perceived read and write latency to the Simba Cloud, and the store perceived latency to the table and object stores. And the y-axis is also in log scale. So as we scale from 1 to 1,000 tables along the x-axis, we also see that the median latency is under 100 milliseconds. And in the 1,000 table case, we find that due to some memory overhead issues with Cassandra, we start to hit some system bottlenecks. So in conclusion, Simba scales to many tables and objects. However, increasing the number of tables becomes a bottleneck, and this is because these storage systems weren't meant for synchronization, and what we really need is some better stores that work for sync. So in conclusion, building data-centric apps should be simple. So app developers should be able to focus on their key value, which is their app's logic, and allow some infrastructure to handle the rest. And we built the S-table abstraction, which manages unified table and object data, guarantees per-row atomicity, and offers tunable consistency. And with that, we built Simba, which is a scalable cloud data sync service that handles data sync and failures transparently. So, by the way, I've been open sourced this code on GitHub, so I encourage you to check it out and provide any feedback. So thank you for your time, and I'm happy to take any questions.
Hi, I'm Mark Shapiro from INRIA. I read your paper. It's interesting, but what I understand is that your consistency model is sort of, you don't provide consistency across tables or across rows, right? There's no system-wide causality or atomicity. So A, is that okay? And B, how would you do it?
So I guess whether it's okay is really, I guess, the setting of what the app needs. So it's something that we definitely want to add in the future to be able to provide multi-row consistency. But however, how we would do it is it's pretty detailed to implement. So I guess it's something we could talk about offline. Yeah.
We have time for one more question.
Do you provide any support for synchronization between peers not via the cloud? So if you had devices on the internet edge that were connected over like Wi-Fi Direct or something, could you achieve consistency in that kind of setting?
Simba just syncs with the cloud store, and all devices sync with the cloud store, so there's no peer-to-peer syncing.
Okay, thank you. Let's thank the speaker.
Thank you.